Hi, good day everyone. Today our group will present our managerial proposal for organizational performance enhancements, focusing on Domino's Pizza Malaysia. Our proposal aims to improve operational performance by identifying key bottlenecks and recommending practical solutions. So this proposal focuses on improving Domino's operations during peak hours. We identified problems such as delivery delays, order inaccuracies, and work inefficiencies. Okay, so our recommendation include improving the process layout, demand forecasting, labor scheduling, and quality management. Next, company overview. Okay, Domino Pizza is one of the world leading pizza delivery companies in Malaysia. It operates under Domino Food Service and follows standardized operating procedure to provide consistent product quality and fast customer service. Input, transformation, and output. Okay, so this slide illustrates Domino's operational system. The inputs include employees, ingredients, equipment, and customer orders. Okay, so these inputs are transformed through pizza preparation and delivery process to produce quality food and efficient customer service. Okay, so core make line process. The pizza production process consists of five main stages. First one is dough preparation, and then topping and baking, cutting and boxing, and finally dispatch. Alright, so every stage must work efficiently to maintain Domino's delivery performance. Process begins with preparing the dough. The dough is taken from cold storage and proof and stretched to the required pizza size before moving to the next station. So next, sauce, cheese and toppings are added according to Domino's standard recipe. Okay, so this ensures consistency and product quality for every customer order. The prepared pizza is then baked in a conveyor oven at a fixed temperature and speed to ensure even cooking and consistent quality. After baking, the pizza is sliced, packed into a box, and checked to ensure the order is complete and accurate before delivery. Finally, the complete order is placed on the dispatch chef and assigned to a delivery rider using the GPS system. At this stage, smooth coordination is essential because any delays will affect the overall delivery time.
My name is Putra Daniel. So now we explain the three main operational issues. First, the cut and box station experience bottleneck due to layout congestion, as you can see here. Second, inaccurate demand forecasting causes ingredient mismatch, resulting in stock shortage and also the excess inventory. Okay. The last one is inefficient labor scheduling lead to longer waiting time and reduced productivity. Okay. So next, to analyze the demand and capacity issue, we evaluated the company forecasting performance using several forecasting indicators. The first one is conveyor utilization, which 97.30% during peak hour. This indicates the conveyor is operating very close to its maximum capacity, leaving very little room to handle the demand fluctuation. Second, we then apply 3 weeks moving average to smooth demand variation and identify short-term demand trend for better production planning. The last one is the forecasting model was evaluated using MAD, mean absolute deviation MAD, measure forecast error where a lower MAD indicate higher forecasting accuracy and more reliable production planning. Okay, so next we analyze the packaging process. The required take time is 24.71 seconds, but the actual cycle time is 38 seconds. Indicate that this workstation cannot meet the customer requirement. Okay, the take time is 34.7 seconds, represent the maximum time allowed to produce one unit while meet customer demand. 38 seconds is the actual cycle time, significantly higher than the take time. This confirms the cut and box station is bottleneck. So the reason is the current workstation layout, the crowded arrangement, increase unnecessary movement, interrupt workflow, and causes process delay. In summary, the production line is constrained by high conveyor utilization, forecasting inaccuracy, and the bottleneck at cut and box station. This finding support the need for process and layout improvement. That's all from me, so I will pass next to next presenter. Thank you.
Okay everyone, my name is Aiza, so let's continue to work measurement and level scheduling. To fix the human resource issue, we design and optimize dynamic labor schedule broken into 4 distinct shifts. The off-peak shift uses 2 workers for low volume. The transition shift ramps up to 3 workers to pre-proof dough. The critical peak overlap shift deploys 5 workers to ensure full capacity execution with a dedicated NZMD line. And finally, a 2-worker wrap-up shift handles sanitation and closing. In order inaccuracy analysis, using a total quality management lens, our 4M analysis highlights that order inaccuracy stems from method, a lack of a dedicated quality checker, materials, poor visual controls under dim lighting, manpower, physical exhaustion due to static scheduling, and machinery, a cramped workspace that violates basic process layout principles. We weighed 3 alternatives to resolve these layout issues. Option A, maintaining the status quo with simple lane markings, requires zero capital but fails to stop driver interference. Option B, buying a second conveyor oven, doubles baking capacity but it's extremely expensive and worsens the downstream packing bottleneck. Option C is a strategic transition to a decoupled cellular layout. Our definitive recommendation is option C, the strategic transition to a decoupled cellular layout. By renovating the storefront to include a physical partition and a pass-through window, we physically isolate the kitchen make line from the dispatch operations. Delivery riders can no longer crowd the packing zone. We will also place a dedicated quality checker at the window to eliminate the 15% error rate. Concurrently, the 3-week moving average forecasting system will be integrated directly into the pulse post, supplemented by a 10% safety buffer. Ultimately, these changes yield improved order accuracy, faster service times, zero driver interference, and optimized labor productivity.
So we go to implementation plan, based roadmap overview. To ensure a seamless transition, we have structured our project into a 8-week pace roadmap. Let's break down exactly what happened during each piece. Week 1 and 2, engineering design and software reconfiguration. We start in week 1 and 2 with engineering and software setup. We will finalize the new kitchen layout, blueprints, and program the 3 weeks moving average forecasting directly into our POS system. So, week 3 and 4, material procurement and staffing adjustment. Moving into weeks 3 and 4, we focus on prep work. We will procure all physical renovation material, publish the new cyclical labor shift matrix, and begin recruiting our part-time crew members. We go to week 5, physical renovation and agronomic overhaul. Week 5 is where the physical transformation happens. To avoid disrupting regular trade, we will construct the protection well, relocate the dispatch station, and set up the dedicated rider zone entirely during off-business hours. We move to week 6, training and operational dry runs. In week 6, we get the team ready. We will conduct comprehensive cross-training for the kitchen crew on our new standard operating procedure and run simulated peak hours trial to stress test the workflow. And lastly, week 7 and 8, full launch and post-implementation review. Finally, is week 7 and 8, we go live with the fully decoupled layout and new shift schedules. We will actively monitor our key performance indicator weekly to ensure everything runs perfectly. So next, we move operational responsibility metrics. To minimize confusion, we are using the RACI metric to clarify roles. It explicitly defines who is responsible, accountable, consultant, or informant for tasks like the SOPs, POS update, scheduling, renovation, and quality control across the position from management to rider. So next, expected performance benefit. Ultimately, the plan delivers 3 major wins. First, isolating the driver cuts our cut and box time from 38 down to a steady 21 seconds. Second, the dedicated quality checker dropped our order defects from 50% to under 2%. And finally, the new forecasting model cuts weekend dough stockouts and waste by an estimated 85%.
Every improvement has risks, so we have planned ways to manage them. We will reduce staff resistance with flexible shift choices and incentive, avoid renovation delay by using experienced contractor at night, and prepare for high demand by keeping a 10% dough buffer. To conclude, our solution focuses on data-driven operation. By improving the kitchen layout, forecasting demand, and scheduling staff better, we can reduce order errors, remove bottlenecks, and consistently achieve the 30 minutes delivery target. This slide lists all the books, reports, and data sources used to support our analysis and recommendations. This layout shows the current kitchen. The highlighted area is where staff and delivery riders create congestion, leading to delays. This flowchart shows the complete order process. It also highlights the cut and bulk station as the main bottleneck causing delays and order mistakes. This diagram shows our proposed layout. It separates the production and dispatch areas to create a smoother and more efficient workflow. This metric compares different layout options based on flexibility, cost, ergonomics, and efficiency. The decoupled cellular layout was selected as the best solution. That brings us to the end of our presentation. In summary, our proposed strategy focuses on improving operational efficiency through a better kitchen layout, more accurate demand forecasting, and improved staff scheduling. We believe this recommendation will reduce delays, improve order accuracy, and help restore the 30 minutes delivery guarantee. That's all for now. Thank you.